Let's take some notes on section 6.5, average value of a function. So these last two sections of our semester are some applications of the integration methods that we know so far. The conversation about how to compute antiderivatives isn't over. It does continue in Calc 2, but for now we're just thinking about some kind of standalone application problems. So our agenda in this section is what you can see on the screen here. We want to compute the average value of some function on a given interval. Typically in these problems, it says the average value, but what they mean is the average y value, right? So the normal familiar scenario would be they give us a couple of y values from some chosen points along the curve. And then let's say they give us 10 y values. We add them up, we divide by 10, that's their average. So the sticky part here is that we know how to do that, but what this goal actually is the average of infinitely many y values, right? Every single y value that's hit on the curve. So we will end up with a formula to do this, but I want to show you a little bit of where that formula comes from. So we're going to start by estimating what that average would be. So we sort of pick out from the interval AB a bunch of kind of representative x values in the exact same way that we would have done for a Riemann sum, right? So they're evenly spaced. So the spacing between them, delta x, is just b minus a over n, where n is the number of little chosen x's. So we're not doing rectangle area, but we're just taking n evenly spaced x values as kind of temporary representatives. So then we would estimate the average of all the y values by just averaging their y values. So we would add up all their outputs, divide by the total number of them, which in this case is just whatever n is, right? So you'd add up, let's say 10 y values, divide by 10, or add up 100 of them, divide by 100, and so on. All right, so this eventually will lead us to the formula that we need. I'm just going to take some time on the side here and solve this formula for n, and then I'll plug it in for n right here in our formula. So I'll multiply it onto the left-hand side and then divide both sides by delta x. Okay, so in the next step, I'm going to write the same average written out, but replace the n with b minus a over delta x. So I have f of x1 plus f of x2, all the way until the last one, f of xn, divided by b minus a over delta x. Dividing by this fraction is the same as multiplying by it upside down. So I can rewrite this with times delta x over b minus a, like that. Okay, so what I'm going to do in this next step is just pull b minus a in any specific example is just a number, right? It's just the length of our interval. So I'm going to pull this out as its own thing, 1 over b minus a. And then what we have left is f of x1, f of x2, all the way to the end, times delta x. We can write this sum in sigma notation, right? This is really similar to Riemann sums in that sense. So we have 1 over b minus a, the sum from I equals 1 to n of f of xi. And now the I is just the subscript of that representative x, right? So f of x1, and then 2, and then 3, all the way to n. And then they each can get that delta x if we consider it distributed in here. Okay, so what are we doing? So what we've come up with is just a fancy formula for what our estimate for the average would be, right? So if n is 10, we're saying pick 10 evenly spaced x values in this interval, add them up, divide by 10. And you might say, well, 10 of them is not enough, right? Get 100 of them, get 1,000 of them, add up 1,000 y values, divide by 1,000. So our exact average y value is going to be the limit of this as n approaches infinity. So the exact average value is the limit as n approaches infinity of the expression above, 1 over b minus a, sum from I equals 1 to n, f of xi delta x. And this should look a little bit familiar. If we ignore the 1 over b minus a term, which is just a number, we have exactly the limit from the Riemann sum section that eventually became the definition for that exact area under the curve, which is the definite integral. So this brings us to our formula for the average value of a function on an interval. So when we're asked to compute the average value of a function, we're going to do 1 over b minus a, where a and b are the interval, and then just the definite integral of the function, because that's what all that limit of sigma turns into. Yeah, so exploring where this formula came from to begin with is kind of a trip, but using it is really straightforward and nice. That's what we're going to do next, is take a look at kind of a representative example from this section. So imagine we're asked to compute the average value of 1 plus x squared on the interval -1 to 2. These are fairly randomly chosen function and interval. They have to give you a function that we are able to do the antiderivative of at this point, so it'll stay kind of within the bounds of this class. But otherwise, there's nothing special about these two things. I do have the graph drawn out here just to give you a sense of what we're doing. We don't need this picture to do what we need to do, but it is helpful. So this green graph here, I don't know if you can tell if it's green, but it is. This is 1 plus x squared. This is f. And then the interval -1 to 2 is marked here. Those are your x values, a to b. So then I have kind of darkened on this graph, all these y values from here to here are what we're trying to average. All right, so our average will be 1 over b minus a, the integral from a to b of f of x. So we have 1 over the length of the interval times the definite integral of the function there. And now it's just computation, right? So I have 2 plus 1 is 1, or 3 rather. So I have 1/3 integral -1 to 2. All right, so to compute this definite integral, I'll do antiderivative, plug, plug, subtract, and then I just have a times 1/3 to apply at some point. 1's antiderivative is x squared's antiderivative is 1/3 x cubed, and I'm evaluating from -1 to 2. Plug in the 2. Plug in the -1. -1 cubed is -1, so that's subtraction. All right, let's make some common denominators. We can do this. It's not too bad. All right, so I want everything over 3. So this 2 will be 6 over 3. This -1 will be -3 over 3. Almost there. All right, 1/3 on the outside still. 6/3 plus 8/3 is 14/3. And then in these parentheses here, I have -4/3. So I have 18/3 in the brackets. 18 over 9 if I incorporate this additional 3 here. So my average value is 2, which reasonably does make sense looking at this image, right? A y value of 2 is right about this height right here. So it is kind of in the neighborhood of this graph. If we got an average value of 100 way up here, or -10 way down here for this graph, that would be suspicious, but this number roughly makes sense given what we're looking at. Okay, let's move on. The other big thing in this section is the theorem you see on the screen here, the mean value theorem for integrals. Pause me at any time to write this down. It says that if f is continuous on the interval AB, then there exists a number c in AB such that, so all of this is saying somebody's y value is equal to the average value of the function. And it's called mean value theorem for integrals because it has so much in common with the original mean value theorem, which said somebody's derivative is equal to the average slope. It has really similar vibes here. So a couple of comments here. One thing, if we say f of c equals this average value formula, sometimes people write this with the b minus a multiplied onto the left-hand side. So if we multiply b minus a over, we get f of c times whatever b minus a is equals the integral. So another interpretation of somebody's y value equals the average value is that this definite integral area, right? This right-hand side is now the exact area between the curve and the x-axis, is equal to, this is height and width of a rectangle. So rectangle area equals, whatever the curve's area is, which is an interesting thought. And I'll show you what this actually gives us in the next example. So we're actually going to revisit the same example from earlier. So earlier in this video here, we calculated the average value of 1 plus x squared on the interval -1 to 2. So we could be asked a question, which I should have written out and I didn't, which is find the value of c. Or why don't we say all values of c, just in case, that satisfy the conclusion of the, I'm going to abbreviate this theorem's name, mean value theorem for integrals. So we'll say MVTI. So this is really reminiscent of mean value theorem questions originally, but here we're looking for a value of c where f of c equals the average value. So that's what we're solving. So we're not setting the derivative of the function equal to anything. We're setting the original 1 plus x squared, or 1 plus c squared, if you like, equal to the average value. So in this one, we already computed the 2, so I'm going to set it equal to 2. In another example, if you hadn't already computed this, this is the first step of the problem. Compute the average value, and then set it equal to the function itself. Okay, so let's solve for x. Subtract 1 from both sides, plus or minus square root both sides, and we get -1 and +1. Just like in the original mean value theorem, if any of the answers you get here aren't in the interval, then you toss them kind of as your last step and you say, okay, that's not one of my answers. So if I had gotten like a 1 and a 7, I would have tossed the 7 at this moment. But -1 and +1 are both in this interval, so I'll keep them both. And let's look at them on this graph here. So in this image, x equals +1 is this point right here. And then x equals -1 gives us this point here. These are the 2 points whose height is 2, which is the average value. So this is my answer to the question asked. The last thing I want to mention is just to revisit this kind of other interpretation over here. So with the b minus a on the left, we're saying there's a rectangle whose area is exactly equal to the area under the curve. So the rectangle that they're talking about in this case, I'm going to go from -1 to 2. And the top of the rectangle is that dotted line at the average value. So the area of this rectangle is equal to this integral right here. So it's possible instead of asking this, they'll say, identify a rectangle with the same area as this integral, and we would just interpret our answer a little bit differently.